So hello everyone, welcome to another particular stereochemistry lecture. So in this particular lecture, we are discussing about some kind of question answers. So I already uploaded the basic stereochemistry lectures. So you will find the playlist something here or here. So today in this particular lecture, we are dealing with some kind of question that type of question can be come in the examination. Okay, so here in this particular module one, we are mainly focused on RS nomenclature, RS, optical activity, and topicity. And after I will upload the lecture of conformers and all, and after we complete our stereochemistry lecture, I will bring a 50 plus questions module where we are discussing all type of question that comes from the stereochemistry part. Okay, so let us bring with our first question. So the first question suggests that the absolute configuration of the compound A and B respectively. So as you know that these two particular compound are nothing but an compound that contains a chiral axis. So we already know that how to determine the RS nomenclature of the chiral axis compound. So we are dealing with the first this one. So it is compound. It is compound of attrop isomerism. Okay. Now here this particular part is bold. That means this group will be the above. So put this NO2 above. So if this part will be above, then similarly this COH part will be below. Okay. So now our rule suggests that first we have to rotate the molecule such a way that this planar group should present in the lower side. So we just simply rotate this particular molecule such a way. So our final molecule would be something like this. COH is here. So after rotating such a way, then the COH will be here and NO2 will be here. Similarly, in our next group, since COH is here, that means this adjacent NO2 will be here and here will be COOH. Okay. Now we have to determine the priority. So between these two groups, so this will be our first priority. Since it is nitrogen, it is carbon. This will be a second priority. Similarly, in this phenyl group, this will be 1, that is nothing but pseudo 3. This will be 2, that is pseudo 4. Now we just put our horizontal one. As the rule suggests that this will be present as it is in the horizontal one. So it is 1, it is 2. Okay, and these two, this particular group should be present in the lower side of vertical bond. That means this here. So the rotation 1, 2, 3 is anti-clockwise in nature. That means this will be a S compound. Okay, and similarly, we just skip down this part. So it will be looking like here, here, COOH, CH3. So our viewing from this side. So between chlorine and bromine, we know that bromine is the highest priority because it's the higher atomic mass. It will be 2. And between these two, carboxylic acid group will be the highest priority. Like it is 3, that is pseudo 3, we are just simply write 3 here and this will be 4. So now if we just simple our Fisher part, that 1 will be here, 2 will be here. Okay, so this away from the observer bond or the dashed bond group present in the lower side 3. So the rotation 1 to 3 is clockwise. Hence it is a R configuration. So the answer will be S R. Okay. So we are complete our first question. So now we are moved to the second question. Second question suggests which compound is the 2s 3s 2,3 dibromobutane isomer. Okay. So simply we just have to calculate the RS nomenclature for the every compound. So here I just want to show one trick. Like for the first A compound, if we take HBr, yes. Now in RS nomenclature, Fisher projection part, there has been a rule that the vertical chain should be the alkyl chain, alkene chain actually. So that means we have to rotate this molecule such a way that this bromine should come in the horizontal bond and the CH3 will be the vertical bond. So Fisher projection one rule suggests that you can keep this particular group constant and interchange this particular group such a way. Okay, so if we interchange this particular group such a way, then our compound will be, this part will be intact. Okay, and here the bromine comes here. H. See, the rotation will be the same direction. Like you don't rotate from here, here, and here, here also. Like the rotation should be in the same direction. Or you can rotate this particular number such a way that this, and this. But if we rotate something like this that represent in the blue line, then what happens? The CH3 not in the vertical position. So that means we have to rotate this way only, the green line position. Okay. So we just rotate simply here. And now we have to check here the RS nomenclature. First priority will be bromine. Now, second priority will be this particular big group, because this particular big group, the carbon contain a bromine, CH3 and hydrogen, and this will be the third. So the rotation of 1, 2, 3 is anti-clockwise, but the H is present, the fourth priority group present in the horizontal bond. Hence, this particular is R. That means one option is wrong. Okay, so just now we move to our second option. Second option, we just do this thing here only. So I just keep this particular down a little bit. Now here we just interchange this. So it will be this particular group I just drawn like this, and here CH3, here H. So I just keep this much more down. Okay. So here, if we do the numbering, this will be one first priority group. This group will be second priority group, this will be a third priority group, and this will be the fourth priority group. So the rotation between 1, 2, 3 is now clockwise, but 4 in the horizontal bond. That means this particular is S. Now we are determining this second part. So here bromine is 1, this particular big group is 2, okay, and this will be the 3. Just this time, this also we have to rotate the particular molecule, but since we have got our S once, then we are just looking for the RS nomenclature. So 1, 2, 3, the rotation is anti-clockwise, and S is H is the vertical bond. That means this also is. So this option is correct. B option. It is little bit of messy, but you will do, then you will get the particular answer. Okay. Now let's move on to third question. The configuration of the two asymmetrics in the C1 and C6 in the bicycle 440 decade, like this particular compound. So first let us draw this particular compound. So this will be our molecule. Now we have to check about the RS nomenclature of this particular chiral center. Okay. So first determine the priority. So this group will be the highest priority because this particular carbonyl group, that means one carbon and two oxygen. One is the normal oxygen, one is the phantom oxygen is connected here. So this will be one. And now between this carbon and this carbon will attach two particular carbon and one hydrogen. And this particular carbon will attach one carbon and two hydrogen. So that means this will be a second priority, this will be a third priority, and the methyl got the fourth priority group. Now here our 4b plus rule suggests that the broken bond calculation should be there, but here the broken bond is not specified. For that particular case, we are using the 4f rule. 4f rule is just a mirrored rule of 4b plus rule that I was not discussed in the class, but here I am discussing. Like what is happening in the 4b plus rule? 4b plus rule suggests 4b plus 3b minus 2b plus 1b minus. And the mirror rule is 4f rule, where f suggests for the front bond or dash wedge bond. That means this bond. Okay. So 4b plus rule suggests this, and the 4f bond is suggest. So this is the 4b plus rule, and this will be the 4f plus rule. Just a mirror rule, like if 4b there plus, then this is the 4f is minus. So here we are applying the rule of 4f minus. Okay. Now we have to check the rotation of the following particular compound. Okay. So if we check here, 1, 2, 3, 1, 2, 3 is anti-clockwise in nature, and the 4 group is the lowest priority group. So 4a plus will suggest 1, 2, 3 is anti-clockwise, and since it is a minus, that means configuration R. So this option and this option is gone. Now we have to check this particular option. Okay. Now I just simply rub it up excess things here. Okay. I just simply rub it up here. Now we have to determine the chirality of this particular center. Now see, between this and this carbon we have to determine the priority. Now here this carbon contains 1, 2, 3 carbon center, but this carbon will show one carbon and two hydrogen. Similarly, this also one carbon, two hydrogen. That means this will be the priority number one. As simple as that. Now, if we go through here, these two chain we are looking for. Here also same hydrogen, hydrogen. Here also same hydrogen, hydrogen. If we move to this point, here also same hydrogen, hydrogen and carbon. Here also hydrogen, hydrogen and carbon. But here in this particular we got oxygen, but here we also only get two hydrogen. That means this chain will be the highest priority over this chain. So this will be 2 and this will be 3 and this will 4, as simple as that. So now we have to check the rotation. 1, 2, 3. Now 1, 2, 3 is now a clockwise and anti-clockwise rotation. Okay. And here the 4 group is the dash bond. That means we are using 4b plus. 4b plus suggests that 1, 2, 3, 1, 2, 3 anti-clockwise, and it is plus, that means S. So the configuration is R1R 6S, and the option will be B. Okay. Now we are talking about next. So this will be an easy question. Like we have to determine the absolute configuration of two chiral center here. So we just simply draw this particular compound. So if this type of simple question is there, like where you have to don't do the rotation to get the highest oxidized chain or something is there, you can directly do your RS configuration from here also. That's not harm. Okay. So here, this particular group is the first priority. Now between this carbon and this carbon, COOH will get the highest priority because here the oxygen is there, but here two oxygen is there. Actually, it is three oxygen. Like if we break the COH group, then it will be nothing COH. That means here three oxygen is there, but here only one oxygen is there. So that means this will be your second priority group and this will be your third priority group. So now rotation 1, 2, 3 is anti-clockwise, and this particular group is the horizontal one. That means this center is 1, 2, 3 anti-clockwise and horizontal, which is R. Okay. Similarly here oxygen. So now let us determine this particular center absolute configuration. So this will be our first OH group. Now between this cyanide and this bromine, this particular carbon contain bromine, that is the highest in molecular mass. So this will be number 2 and this will be 3. So the rotation 1, 2, 3 will be clockwise, but this particular hydrogen present in the 4. So that means the configuration is S. So this is the correct option. So go for the next question. So here we are getting on compound and we can easily see this is our chiral center. Okay. Now the stereochemical, and also here is a double bond is there. That means we have to determine the EZ nomenclature also. And we already know if there is cis, then it will be a Z nomenclature. If it is a trans, then it will be the E. Okay. Now here all are the E and Z are present in the 2. That means we are not bothered with the IUPAC naming here in this particular question. Just we have to find that this particular group is cis or trans. Okay. Now if we see here, okay, if we see here, this group will get highest priority over this group. Similarly, this particular acid group will get highest priority over this methyl group. So that means the both the highest priority group of each carbon center present anti to each other. That means it is a trans molecule, and trans molecule we are the naming is E. That means this two option is gone. So now this two option is there. Okay. Now we just simply draw this particular molecule brief way. Okay. So now we are just naming. Obviously, OH will get the highest priority. Now this particular carbon contain carbon and hydrogen. Here this particular carbon contains the same hydrogen, carbon and carbon. Okay. And this particular carbon contains a carbon and also a carbon. This is the phantom carbon due to this particular double bond. Okay. So this chain will getting the highest priority over this chain since this particular center are equivalent. So we are moved to this particular center, and here if we go on the subsequent centers, so it will get 3 hydrogen. Here 3 carbon is there. That means this will be our 2, this will be our 3, and this will be our 4. Now here in this particular question, we are actually using both of the rules, that the 4b plus rules as well as the 4f plus rule. So we are using here 1b minus rule. Okay, for simplicity, since we are learn about the broken bond rule or the back bond rule, so we are just stick with that particular thing. Okay, and so here we have to check the rotation 2, 3, 4. 2, 3, 4 is nothing but a clockwise rotation. but the rule suggests it's negative. That means the configuration will be S. So this will be the correct option. 2E 4S. Okay. Now move to this particular question. Again, we have to do the same RS nomenclature. So just draw this particular group. This also possesses an axial plane, axial chirality plane. Okay. So just we have to determine the naming. This will be the first and this will be the second. Similarly, this will be one, that is pseudo 3, and this particular group will be the 2, that is the pseudo 4. Now, as rules suggest that we have to rotate this particular molecule such a way that these two groups are present in the horizontal one. So we just rotate something here like this. So these two group will be in the plane of paper. Now we just simply putting the value like 1 is here, 2 is here. Okay, and this particular group present in the away from the observer bond, so it will be here. So now we check the rotation 1 2 3. 1 to 3 is clockwise in nature. That means this will be a R. This will be R configuration. And plane of symmetry is not here, because if it is a plane of symmetry is there, then the particular molecule will be not chiral at all. Okay, so plane of symmetry is not here. S configuration is not here. Center of symmetry is not present in the axial chirality. So that means there is only one option is correct, that is the R. Now again we have to do the particular RS nomenclature of this particular compound. So just simply draw. So simply this particular molecule is looks like this. So what happened that we have to rotate this molecule such a way that this group will present in the downside. So I just simply rotate. Okay, I just manually rotate this particular molecule. See, the if I rotate something like this way, so this particular OH should be present in the right hand side, and this will be present in the left hand side. Similarly, if the hydrogen is present in the left hand side, that means the methyl will also present in the left hand side, and this particular ethyl is present in the right hand side. Okay. Now we are numbering 1 2 1 3 2 4, and our angle of viewing is something like this. So if we put here 1 2, this particular group should be down. Okay. So now 1 2 3 is anti-clockwise in nature. That means it is a S. And similarly, if we look upon this particular compound, I just do once directly, like we have to rotate this particular group such a way that hydrogen will be here, and since hydrogen is there, that means this particular bonded hydrogen is also here, and the bromine will be here. Now between these two, this will be the highest priority, this will be the second highest priority, this will be the pseudo 1, that is a pseudo 3 priority, and this will be the pseudo 4 priority, and our viewing is from here. So putting this all together, 1 2, this will be again down, this will be, so the rotation 1 2 3 is clockwise, that means R. So the option will be SR. Where is the option SR? This option, the SR. So this will not. This is the correct option. In our next question, we are talking about that determine the absolute configuration of these two compounds. Okay, so just simply draw this particular compound little bigger. So when you are doing this particular question, you have to be a little bit cautious. Like this type of question are giving free marks to you. So don't do silly mistakes in this type of questions. Okay. First determine this chiral center. So this is nothing but a diastereomer, simple things. Okay. So this will be the first priority group. Now between methyl and this particular carbon, this carbon will directly connect to the bromine center. So this will be our 2, methyl will be 3, and this is 4. So we are simply applying 4b plus. The rotation of 1, 2, 3 is what? This is clockwise. So that means this is R. Now here this is the 3. That means 3R is correct. This 2 is wrong. So this is a 3R. And this is the second center. Please be remember this type of things because this type of thing is sometimes confusing and leads to erroneous results. Okay. Now here we are talking about this. So this will be the first priority group. This will be now the second priority group. Why? Because as I already discussed in the previous class that these are the carbon that contains 3 oxygen group. So this will be the highest priority. Here is only one oxygen group is there. So this will be the third priority. And this is the hydrogen. There is a fourth priority group. So now we are looking about the rotation. We are using here 1b minus. So the rotation of 2, 3, 4. 2, 3, 4 is anti-clockwise in nature. But since it is a negative sign, that means we are talking about this is uh, anti-clockwise, but it is R. So that means the option is 2R, 3R is the correct option. This also R, this also R. Okay. So now we are moved to our next question. So here also we have to determine the RS nomenclature or absolute configuration. For from this is the this carbon, and from this is the this carbon. So we are first talking about this particular carbon because it is looks easy. Here you can see this particular group. I just open up this particular. I just open up this particular triple bond to other phantom atoms. Similarly, I have to open this particular also. See, this all have a phantom atom. Whenever you find a bond, so the phenyl center is looking like this because this also generate one phantom. This also generate one phantom. Okay, and this also generate one phantom. So the overall molecule is look like this. Now we are determine the priority. So this is in the first priority. Now we are talking about this two center. Like if this center, if we're looking about, this contains 3 carbon. This particular center also contains 3 carbon. Okay. Now in the second, so this will not our determining center. So we are further move to a second carbon. This also connected 3 carbon, but here this connected with 1, 2, 3 carbon, 1 2. So we're not looking for this particular bond here. So here 1 2 3, 2 carbon, 1 hydrogen is there, but here it is a 3 carbon connected, direct connection. We are not looking for this particular carbon connection because this also carbon, this also carbon. So this will be the highest priority. 3 carbon, 2 carbon, 1 hydrogen. This will be the highest priority. So this will be the third priority. This will be the fourth priority. So since fourth priority group present in the vertical bond, that means the rotation of 1 2 3 is anti-clockwise in nature. That means this carbon is S. So we have to find the answers where the S is there. So these two are not there. So we just simply eliminate the options. Now we are just determine this particular carbon. See here 1 2. In the second part we get oxygen. Here 1 2 3. 3 rotation on the exchange. So between these two carbon, this carbon will be the highest priority. Okay. So this also we get 1 carbon, then oxygen. Here 2 carbon, then oxygen. 2 hydrogen is there. So here CH2, just simply draw this particular molecule. Okay, otherwise it will be a little bit confusing. I just simply remove. Okay, so now we have to determine this particular compound. Now we have to determine the priority order between these two. If we put it as 1, this will 2, this will 3, this will 4. So this will be the 2F minus 2B plus 1 3 4 is clockwise. Hence R. So the option is this. Okay, so now we are moved to our next question. Okay, so we are just beginning with our optical rotation questions. So this is the first question on optical rotation. So what is the given in this particular question? Like we have to define the specific rotation of a mixture that contains 30% of -2 bromobutane and plus 70% of +2 bromobutane enantiomer, and given that alpha D of pure enantiomer is minus, for minus compound is 23.13 degree. So what is given? First we write of minus. Now this thing you have to remember very cautiously. If it is given alpha D of pure enantiomer, that is 23.13 degree, is minus, then alpha D of plus pure enantiomer should be plus 23.13 degree. This thing you have to be very much, you have to remember this particular thing. Okay, like if alpha D of minus is given there, then alpha D of pure plus will be the exactly opposite, just sign will be changed. Okay, this will be remembered. And here it is given that 30 mixture, 30% of minus and 70% of plus enantiomer is there. So we just simply determine the enantiometric excess, that is EE. E is nothing but 70 minus 30. 40%. Now the rule suggests, sorry, alpha Sp of mixture equal to alpha pure into E. This is the rule to determine. Please remember this rule. This rule will be very much repeated during this type of questions for mixture. So our value is there. Now you see 40% is plus enantiomer is excess, because 30% is minus, 30% of minus will take 30% from here plus to make a racemic mixture. And if they are forming the racemic mixture, that means this part will not affect the optical activity. So the rest 40% of plus will lead to optical activity. So we have to use this particular value for alpha D. So 23.13 E by 100. If it is in percent term, then you also put the simple 40 by 100, or you can write E by 100. Okay. So into 40 by 100, and we just simply calculate these values to get our desired. So it is 9 point plus 9.252. This will be our value. Okay. So this will be our final value, and this type of question comes in the NET examination. So you have to write whatever digit they are asking. Okay. If it is a 2 digit, then you will write plus 9.52. If it is 3 digit, then 9 point, sorry. So if they are asking about the 2 digit, then you are 9.25, and if it is 3, then it is a 252. That's all. Okay. Now we are moved to our next question. So the next question says that an aqueous solution of an optically pure compound of concentration in 100 milligram in 1 ml water and measured in the quartz tube of 5 centimeter length was found to be 3. So just we are taking specific rotation formula alpha Cl. I hope you remember this particular formula. We are talking about our optical activity lecture. So here alpha is given -3 degree. Okay, concentration always be gram per ml. Here it is written 100 mg. 100 mg means 0.1 gram. That means 0.1 gram per ml. Since it is a 1 ml of water, that means gram per ml. And quartz tube L 5 centimeter. But I hope you remember that when we are dealing with optical activity question, we are taking in a decimeter scale. So this will be the 0.5 dm. So hence we are determining the alpha Sp. So let's determine. So it will be -60 degree. Okay. So like this we have to deal with this type of questions. Now in the next question, it is given that calculate the optical rotation of the following given. Sp is given, that is the, I think it will be our uh, alpha dpo. Okay, and d and l is there. So enantiometric axis we have to determine 90 minus 100, 90 minus 10 divided by 90 plus 10 equal to 80%, or 80 by 100. So the optical rotation Optical rotation is nothing but a specific rotation that I already discussed. E, if it is written like this and if it is percent, then it will be E by 100. So 20 into equal to 16 degree. So this will be the answer of this particular question. Okay. And now move to the next question. Next question suggests that tartaric acid have a specific rotation of plus 12 degree. So it is given that alpha sp pure plus 12 degree. Okay. So now in the mixture, this plus tartaric acid present in the excess. That means we don't need to determine the minus pure alpha sp of pure minus tartaric acid. That is nothing but a minus 12 degree. That is not required for this particular question. Now we have to determine the E. E is 68 minus 32. 68 plus 32. Major minus minor divided by major plus minor. So the value will be the value will be 0.36 or 36%. Okay. Now, and this will be due to the plus tartaric acid. So we just determine the alpha D equal to alpha sp pure into EE, and if it is percent, then if percent E, then E by 100. So we just simply put the values here. So it will be our 12 into E is 0.36. So it will be plus 4.32. So this will be our answer. Okay, for this particular question. Now we are look about the second question. It is written dextrorotatory alpha pinene has a specific rotation value. So this will be our pure. A sample of alpha pinene containing both the enantiomer was found to have a specific rotation value of this. So we have to determine the percent of the enantiomers present in the sample for the plus, I think. So this will be a very easy question. Like when it will be the plus enantiomer present. So first we are determine the EE, enantiometric axis. Now simple here, I just want to tell you about one thing, that since it is given the dextrorotatory compound have the pure value, this is the plus, and after racemic mixture formation this value is still plus. That means the dextrorotatory value will be the major in this particular mixture. So we just simply determine the E. E is nothing but that alpha observed by alpha pure. Okay, that the pure. So that means 30.8 30.8. So it will be 0.60 or 60%. That means enantiometric is 60% suggest that the mixture plus enantiomer plus enantiomer 60% and 40% for racemic. Now dextrorotary, I have determined the dextrorotary is plus enantiomer, okay, and 40% racemic. And out of this 40%, 20%, sorry, the 20% will be the plus enantiomer, and the rest 20% will be the minus enantiomer. So overall, plus enantiomer will be 60, that is the excess, plus 20%, which are formed in the racemic. This will be the excess, and this will be the racemic. So 80%. So the answer will be 80%. Okay, so by this you have to do this type of questions. Now, I think this will be the final question of optically pure isomers. So it is written that optically pure compound X give a specification of plus 20, and mixture of X and its enantiomer Y gives us plus 10. So similarly, we have determined the E. E is nothing but a alpha observed by alpha pure. So 10 plus 10 plus 20, 0.5 or 50%. And since there is a plus is plus, that means X in excess. So from the E, we conclude from the E value, we conclude that mixture 50% X and 50%. This is the excess racemic, due to which 25% will be X, 25% Y. So that means overall mixture contains 75% X and 25% Y. So if we determine the enantiometric ratio, ER will be 75 is to 25. That means 3 is to 1. So we have to determine the A plus B. So A plus B is 3 plus 1 equal to 4. So the answer is 4. Okay. So this is the another interesting question. This type of question can become in the examination. So now we are discuss some kind of topicity question in brief. So find the topicity of the following groups. So first we are talking about this particular group. But before discussing about topicity, let us recapitulate that what is the rule. So to determine topicity, there is two different rules there. One is the addition substitution criteria, and one is the symmetry criteria. For the most complicated question, we are using symmetry criteria, and for very little question, we are doing addition, subtraction, addition criteria, because in the examination time we have don't much enough time to do that substitution elimination criteria. So first, just I write the simplest rule here. If two group can be separable by C2 symmetry, then it will be homotopic. If sigma I Sn symmetry, then it will be the enantiotopic. If no symmetry, then it will be a diastereotopic. And another thing is, if any compound contains adjacent chiral center, then surrounding group will be diastereotopic. Similarly, prochiral center group will be enantiotopic. This will be the very much summary of determining topicity. So just write down all those things, and after that we will discussing about the question answer. So I just simply remove this particular thing just to remind you these things. Okay. Now we just deal with this particular questions. So see first question here. See, this will be a chiral center. Okay. And here we have to determine this two particular group. So since it is already present a chiral center, so adjacent carbon groups are diastereotopic in nature. And if we go with the symmetry criteria, see these two particular HA and HB, between this there will be no symmetry present. That means it is also a form of diastereotopicity. Now, if we look about this particular compound, see this is already present on a chiral axis. That means these are actually a chiral center is there. So here this HA and HB, this also diastereotopic. Since already a chiral center is present, so adjacent group will be diastereotopic in nature. Similarly, these two also don't possess any kind of symmetry between them. So that means this also diastereotopic. Here in this particular question, okay, we have to determine the relationship between these two methyl center. Now, in symmetry criteria, there will be no symmetry element present between two methyl group. So these two also diastereotopic. So these three are diastereotopic in nature. Next, we are moved to this particular groups. So here we have to determine these two groups. So we just simply draw like this, HA, HB. Now here both the methyl group in above and the hydrogen is below. So if you see closely, then we can see that it contains a plane pass between these two groups because these two are mirror image to each other. That means this HA and HB are enantiotopic in nature. Here in the next question, if you see that this HA and HB are interchangeable by C2. Like if we just flip this particular group, then the group will be this will be similar H H HA Cl Cl HB. So this is by interchangeable by C2. So that means these two are nothing but enantiotopic in nature. Sorry, homotopic in nature. Now, what happened for this particular group? If you see here, this center, first of all, if we go for the symmetry criteria, then we can say that these two groups are actually no symmetry element present in this particular group. That means these two are diastereotopic in nature. As simple as that. But if you go on the addition substitution criteria, then you can see that if we change one of the H with any kind of substituent, let us say D, then this particular center is also become a chiral center. Now, if this particular center become a chiral center, and here is also a chiral center present, that means these two are forming a diastereomer. Okay, because if we put D change, if we change HA by D and HB keep intact, that doesn't harm this chiral center absolute configuration. That means it will form a diastereomer. That means this HA and HB are nothing but a diastereotopic in nature. Now let us move to this particular compound, HA and HB. See, if we see firmly that these two are also changed by us interchanged by a C2 symmetry, or if we do the simple addition elimination addition substitution, HB to BR and HA to BR, then these two are nothing but the same molecule. Like if we rotate this 180-degree, we got this same molecule. That means these are homotopic in nature. Now simply these two are nothing but a homotopic in nature, since this also be interchanged by a C2 symmetry. But here in this particular question, these are not homotopic because the double bond is there. So here no symmetry present. Okay, so in the next question, we have to find the topicity of the following ligand: HA, HB, and HC. Now we are doing simply the symmetry criteria. Like if you see here in this particular case, okay, HA and HC, between HA and HC, we simply see a plane. Okay, plane of symmetry. Like this plane contains these two group also here. So these two are nothing by the mirror image relationship. Now you may say that why not C2 symmetry? Like if we do a C2 here, then it will not become a same molecule. Like if we do C2, just draw here. If we do a C2 symmetry, then the ring will get flipped. So not exact molecule is getting here. So this will be the enantiotopic. And between HA and HB there is no relationship is there. That means this will be the diastereotopic. Next question. Um, for the next question, see these two HA and HB are simply the same compound. HA and HB are homotopic in nature because if you see the skeleton, this skeleton are simple like this particular skeleton. That means this HA and HB are interchangeable by C2 symmetry. That means this HA and HB are homotopic in nature. Similarly, if we see about HC and HF or HD or HE, then we can imagine a plane here. And by this plane, these groups and these groups are become a mirror image relationship. That means this pair will be enantiotopic in nature. Now, if we talking about HC and HD or HE and HF, then there will be no symmetry present at all. So that means this pair will be diastereotopic. Okay. So with this, we have to end. So thank you for your time and support. Okay, so we have completed the 20 plus questionnaires in this particular video, and from the next lecture we are starting with our conformational analysis. Okay, so thank you for listening.